Well, let me introduce myself a little bit. Actually, I lived in the Dayton area for about 20 years. I cut my teeth during the Reagan administration, during the Star Wars initiative. I worked at Wright Pat for a number of years, and now I'm at West Virginia University working on coal conversion, but I'm still intensely interested in space exploration, and I wanted to share some very preliminary simple thoughts about implications of water on the moon and what that means for interplanetary exploration. And basically, there have been news blurbs over the years about water on the moon, and when I saw that, I thought to myself, that sounds a lot like rocket fuel. And so with that, let me mention that I think this is probably something that people in the audience are generally familiar with, and there have been different degrees of claims that have been made over the years, where first they detected hydrogen, then they were able to determine that the chemical state of that was indeed water. Some of the theoreticians sat down and calculated that if you were in a properly sized lunar crater that was shielded from the sun, it could stay cold enough that you could maintain water in such a crater for a very long time, because the vapor pressure of water can be low enough that it doesn't evaporate like your intuition might tell you. So people started to look for water in craters, and lo and behold, they found it. Within the past calendar year, NASA has published estimates that there are millions of tons available, and that much of it can be accessible by a lunar base that might be built there. And so what I thought about was, well, could we electrolyze water? Could we make propellants, and could we transfer that to useful places such as low Earth orbit or perhaps Mars orbit? And would that facilitate the ability to explore Mars or to send spacecraft to other faraway places? And then when I did that, I started getting into the economics a little bit, and I realized that there might be the beginning of a notion for how a cash flow positive economy might be built on the concept. So that's basically what I'm going to explain today. This is a map of the Earth-Mars system in terms of delta V, in other words, how much velocity you need to impart to a spacecraft in order to reach your destination. I cobbled this from Wikipedia, and I think it's basically pretty accurate, but what I wanted to point out is that if you look in the lower left-hand corner, the major investment is getting into low Earth orbit, which requires something like 10 kilometers per second, whereas it's not so tough to get there from the moon. And when I'm talking about electrolyzing water, it's the same thing that we're talking about, so that a child born today might have the first spaceship that he drives at age 16 would be powered by a fuel cell or electrolyzer. We're just taking water and using electric energy in order to separate it into oxygen and hydrogen. That's all I'm talking about. And this is something that NASA has considered for a variety of reasons. They were thinking about how they might power a lunar base during dark side operations. Solar power is great, of course, when the sun is shining, but on the moon you have to subsist somehow for 14 days while you're on the dark side. And so they thought, well, maybe we can use electrolysis in order to supply hydrogen and oxygen, which could be recombined in fuel cells or other the energy conversion equipment of your choice. And so there have been studies on these concepts, mainly in the context of powering a lunar base. And this, by the way, is the salient event that occurred within the past year, and we're thankful and impressed by NASA's discovery using a miniature synthetic aperture radar, which was contained on an Indian payload, and identified more than 40 craters which are harboring significant quantities of water ice, and that the total quantity is in excess of millions of tons. And so I'm saying, well, let me just take some of that and electrolyze that in order to make rocket fuel. By the way, 1 million tons is kind of like the capacity of a small coal mine, if I can use a West Virginia analogy. And then what I'm talking about is an analogy to mid-air refueling. This is a Air Force operation where the Air Force flies. They can't necessarily have a gas station where they want one, and so they take theirs up into the air, and they bring a tanker close to an aircraft that they wish to refuel, and they have means to inject propellant into the aircraft while it's flying. And so I'm talking about something like that, except for satellites and spacecraft. And the notion is that you would bring liquid hydrogen and liquid oxygen to low Earth orbit, and that you would fuel up, like let's suppose that you had a communications satellite. I'm saying take the upper stage empty and then fill it with liquid hydrogen, liquid oxygen once you get to low Earth orbit. That formula could be used for geosynchronous satellites or other satellites that require large altitude changes or attitude changes for whatever reason, or from the standpoint of those of us interested in space exploration to Mars and beyond, this is a possible way to fuel deep spacecraft without having to carry the upper stage fuel. And this is made possible by the lower delta V from the moon, the Earth's moon, to low Earth orbit. And the calculations based simply on first order Tsiolkovsky analysis show that a payload from the moon might have a spacecraft launched from the moon to low Earth orbit might be able to take 30% of its initial launch pad weight to low Earth orbit. By comparison, if you're talking about earthbound systems, a good figure of merit might be something like 3%. So in other words, if you take a rocket, put it on a scale and weigh it at the launch pad, about 3% of that weight might be useful payload by the time you get to low Earth orbit. The other interesting factor is that if you have a reusable system, and of course the space shuttle engines were reusable, but let's suppose, if you'll humor me for a moment, that you have a capability to reuse a tug that would go back and forth between low Earth orbit and the moon's surface. Well, that would directly impact the original launch cost. It was very costly to send things all the way to the moon. But if you could reuse it many times, once it gets to the moon, then the effective launch cost is reduced, and it's a simple linear relationship between the number of times you can reuse it and what you have to pay in order to get it off the launch pad from Cape Canaveral. So if you had an engine that could be reused 100 times, that means that the normalized launch cost also goes down by a factor of 100. So these kind of factors of 10 and 100 are the type of factors that you need in order to change the way that we think about space exploration. And by the way, I should also mention, since this is the Mars Society, that this idea about using indigenous propellants is not a new thing, but the president of the Mars Society, Bob Zubrin, of course, has been the chief architect of the notion of using in situ resources on Mars. And I think if there were such a thing as a Nobel Prize for engineering, that Bob should get that, because I think it's one of the greatest ideas that I've ever come across in my professional career. So I'm trying to emulate Bob to some extent in this presentation. Well, anyway, so once I started to think about sending fuel back and forth between the moon and low Earth orbit, one thing that's obvious is that on an energy basis, that the moon would be favored over the Earth as a launch site for transferring fuel back and forth. If you were to imagine for the moment that you had a continuous megawatt of enthalpy generation at some future lunar base, that translates to about 600 tons per year of propellant to low Earth orbit. And so then I thought, that actually gives you a basis to compare revenue, because if you imagine that in the future that spacefaring entities create an economy in which these entities continue to operate spacecraft and to do the types of things that we're talking about, then it will save them money if they can undercut the price that they have to pay for fuel. And by the way, that price is almost all launch cost. The actual price to produce liquid hydrogen and liquid oxygen is pretty pathetic. It's very, very small. It's all launch cost for the users. So I'm saying, well, okay, if you're paying $5,000 to $10,000 per kilogram now, maybe in the future, prices will go down, but maybe there's a sustainable market for $2,000 per kilogram fuels. And if that were true, then the revenues from an operation like this would be worth about $1.3 billion a year. And what that suggests is that perhaps at some point cash flow positive operation could be contemplated for space. You might save more money by operating this fuel shuttling operation than you would pay by relying on bigger launch vehicles or more launches from Earth. Okay, so having made that observation, then I started to think a little bit about what does it mean to talk about economics in space. And I'll confess at the outset that I really don't know. I have a hard enough time understanding the economics here on Earth, and especially in the United States. They talk about the gross domestic product, or GDP, and I think I have an idea sort of what that means, but it may not be a perfect description of the wealth of a country, but we understand that it has to do with consuming goods and producing goods and services within a country or an entity. And so if we take that same concept and apply it to space, what we would mean is if we wanted to have an organization or an entity in space that had a high GDP, you would want to be able to consume goods and services, and the one basis that I could find for comparison would be rocket fuel as a commodity. Some people have talked about such things as mining asteroids. For example, maybe you could find an asteroid that had platinum ore, but I thought, the problem with that is that there just aren't jewelry stores in outer space. We don't really have a market or place to sell that stuff. So either you have to bring it back to Earth, or the value doesn't make any sense. But if you talk about rocket fuel delivered to low Earth orbit, there's a common parameter by which you could construct the beginnings of an economy in space with. And so for that reason, I'm saying, well, where would you go if you wanted to make it easy for yourself to consume a lot of energy? And I thought, man, I think I'd probably want to stay out of the gravitational wells for the Earth and Mars. And so maybe I would want to spend most of my time in orbit and only go down there if I had to do so in order to operate a factory or something to produce fuel. But if you could, you'd rather stay in orbit and consume energy at that point.